Okay, this is our last, or maybe second to last video, depending on how much I get through of this, on conservation of energy in pendulums and springs. Second, or possibly last video for the energy unit. And this, especially the pendulum part, is one of my favorite applications because you get to do a lot of kind of neat math and physics with pendulums, especially, and springs as well, but pendulums mostly so. So we'll start with a pendulum question. The above drawing shows a simple pendulum bob of mass m on the end of a string of length L that has been pulled back to an initial angle theta naught from its equilibrium point and then released. The pendulum experiences negligible amounts of friction. In terms of the given variables, that would be m, L, and theta naught, and any fundamental constants necessary, determine, number 1, the initial potential energy if UG equals 0 joules at the lowest point in the swing, 2, the maximum speed of the bob, and 3, the tension in the string at A, its initial release point, and B, at its lowest point. So, the first important thing to notice is it says that we have negligible amounts of friction. What this is really trying to get us to understand is that ET doesn't change, and we are to use conservation of energy. So that's the main principle we're trying to use. Conservation of energy. Great. In other words, ET up here equals ET here, which is equal to ET here. The total energy never changes because no energy is ever lost to friction. If this was indeed the case, this pendulum would swing back and forth for forever. Okay, so let's try number 1. The initial potential energy if UG equals 0 joules at the lowest point of the swing. So if UG is 0 here and we bring this up, how much gravitational potential energy is there? So what we really need to know, if you think about the gravitational potential energy equation, it's equal to mgh. Mass is given to us. G is a constant. We can use that. But what is h? If the top of the pendulum is, if the top of the bob is here, and then at this point it's up here, then what we're really looking at here is this height h. And h is not one of our given quantities. So we need to figure out, well, how are we going to determine what h is? There we go. How do we determine what that h is in terms of the other variables that we know? So we want to know how high above the lowest point is this. And we know that ultimately we're going to get an answer that starts with m times g. We just need to figure out another way of writing h in terms of the variables that we know. What I would do is encourage you to write out some of the other things that we know. These this solid line represents the string, and these dotted lines also represent the string. And we know the string's not changing in length. So this is L, and then this whole entire thing here is also L. So if you see here, what we actually have is a little right triangle formed by this horizontal dotted line that shows the highest point that the bob gets to, L, the string at that point, and then this, the string when it's moving, when it's hung straight down. How big is this right here? Okay, how big is that? Well, if this whole thing is L, and the part that's not included in this is H, doesn't this have to be L minus H? And in fact, it does. This side of the triangle has a length of L minus H. This side of the triangle, the hypotenuse, has a length of L. By the way, that's a little right angle right there, isn't it? So interestingly, we can actually use trig to come up with an expression for what h is based on this side length and this side length and the angle that we're given. The angle's here. This is the hypotenuse, and then this is the adjacent side. So if you remember your trig, then the cosine of theta naught, the angle up here, must be equal to the adjacent side over the hypotenuse. The adjacent side is L minus h. The hypotenuse is just L. If I cross multiply, I get down to L cosine theta naught equals L minus h. And if I solve for h, I add h to this side, I subtract L cosine theta naught over to the other side, I get h equals L minus L cosine theta naught. And I have an L in both these terms, I might as well pull this out so that I have L, parentheses, 1 minus cosine of theta naught. Just a little bit more simple. Now, what can we do with this? Okay, does this make sense? What this is saying is that the height that the pendulum is pulled back to depends on theta naught. Okay, L is just the length of the string. That's going to be a constant. Depending on what the angle is, we get different heights. Let's say we don't pull it back at all. Let's say that the angle we pull it back to is 0. The angle we pull it back to is 0, then the cosine of 0 is 1. And I'd have 1 minus 1, which is 0, times L, which is still 0. H would not be any different because we didn't pull it back. What if I pull it back to 90 degrees? Well, the cosine of 90 degrees is 0. I would have L times 1 minus 0, or L times 1, or just L. That would mean it's at a height of L, and you can see that if I were to pull this string back 90 degrees, it would be the length of the string above the initial spot. Let's do one more. If I were to pull it back 180 degrees, that would mean that I pull it back all the way to up here off the screen. The cosine of 180 degrees is negative 1. 1 minus negative 1 is 2, and I would have 2L. So if you think about it, that would mean you're taking this and pulling it up this far. That would definitely be 2L, so this expression seems to make sense. So my height here is going to be L times 1 minus cosine of theta. So the expression for the initial potential energy, depending on how high it is pulled back, is mgl 1 minus cosine theta naught. Nice. So that's the initial potential energy. Number 2, the maximum speed of the bob. Where will that be reached? Well, if we have this pendulum system set up, we're transferring gravitational potential energy and kinetic energy back and forth. So we want where the gravitational potential energy is going to be minimized so that the kinetic energy can be maximized. That's very obviously at the lowest point in the swing. So we're going to set up our conservation of energy equation, where the first part, the left-hand side, the initial side, is going to be when the bob is all the way pulled back. The bottom is going to be when it swings through the lowest point. So we're going to write UG naught equals K. I guess I should have had UG naughts there too. So UG naught we just solved for. That's mgl 1 minus cosine theta naught equals, we want the speed, so the equation for kinetic energy is 1/2 mv squared. I have an m on both sides of my equation. I could divide those out. And then all I need to do, multiply both sides by 2 and take the square root. So v ends up being the square root of 2gl 1 minus cosine theta naught. And that's the speed of the mass of the bob as it passes through equilibrium. Again, notice the bigger the angle gets up to 180, the bigger this argument is inside the parentheses, so the bigger the speed will be, which makes sense. If you pull it all the way back to 180 degrees from its initial position, it'll move the fastest when it goes through. So there's 1 and 2 answered. For number 3, so, okay, let me step back a second again. So the initial potential energy and the maximum speed we got just by doing energy. When it starts asking us, in this case, when it starts asking us about forces like tension, now we need to do something different. Now we need a free body diagram. Okay, so we need forces. We want the tension at the initial release point. Okay, so that's when it's here. So let's draw a free body diagram for that. So 3A, we have a free body diagram that looks like this. Here's our bob. We have, let's see, tension extending up this way. And we have gravity down. Oh, and I forgot to put my axis. And there's a question here, which way should you orient your axis? Should you make it so that, should you make your axis so that it's the standard y up and x to the right or left, or should we do something else? In this case, the pendulum is actually related to circular motion. And the reason a pendulum is related to circular motion is, imagine the shape that this pendulum bob would trace out if you allowed it to go all the way around. It traces out a circle. Just because it doesn't go all the way around does not mean that it's not tracing out a circle down here. So the pendulum is actually in circular motion as the entire time that it's moving. So what we want to do, actually, even though it's not moving where the bob, not moving at the initial release point, we want to orient our axis as if we were dealing with a circular motion problem. And what that means is making sure that we have a direction that points along the direction towards the center of the circle. So I'm going to align my axis like this. where the direction towards the center of the circle is C, and I'm just going to call the other one X. Looking at it this way, I can see that tension points in the direction towards the center of the circle. FG, however, we have to split up. So I'm going to split this up into components. Okay. Now, I need to find my angle. Well, if you look at our free body diagram, this angle right here between FG and this component that is in the opposite direction of tension looks just like this angle, where we have the line going straight down that is in the same direction as FG, and the tension and the line when and the string when the ball or the bob is up here. So this, by inspection, must be theta naught. Therefore, this is FG cosine theta because it's the adjacent component. This must be FG sine theta naught. Now this would have been tricky to do had we not aligned our axis like this. If we had done our standard axis, that is fine, but we would have had to deal with some acceleration in the y direction, and we don't really know a lot about that acceleration, so that would have been kind of tough to do. In this case, what we can say is that in the c direction, because we're looking for the tension, we have t minus fg cosine of theta equals mac. And we can rewrite that as tension minus mg cosine theta naught equals mv squared over r. But wait, at the initial release point, is the object moving yet? Is the bob moving? Not at all. This entire term must be 0. Therefore, our tension at the release point must be mg cosine theta naught. There is some acceleration in the x direction, but that would be a lot harder to find. That would be a little tricky. And that acceleration changes the entire time. Okay? So it would have been a little difficult to do if we didn't orient our axis like this. A more common problem is given in 3b. What's the tension in the string at the lowest point? Well, at the lowest point, the free body diagram is actually a lot easier. We simply have tension up, we have the force of gravity down. Oh, I probably should put in, here's the bob. Here's our axis. We still want to go with the idea that this is circular motion, so the positive c direction points along the tension. And we'll just make the x direction. Oh, well, let's be consistent at least. Let's make it this way, just for the heck of it. Okay? Now, we still want to know what the tension is. So we write Fc equals T minus Fg equals MAC, and we know that AC equals V squared over R, so we write MV squared over R. R being the radius, V squared, or V being the speed. So we have tension minus mg. We can't cancel this out this time because we know that the speed at the lowest point is this. We already found that. So we're going to write m times the square root of 2gl in parentheses 1 minus cosine theta naught. That whole thing is getting squared over r. What's the radius of the circle that this object is making? It's L, isn't it? Over L. So something interesting is happening. I have t minus mg. I'm squaring what's in a square root. So that means the square root just disappears. Equals m times 2gl 1 minus cosine theta naught over L. Which means this set of L's cancels. And interestingly, I'm going to add that mg over to the other side. Now I've got a bunch of algebra to do. So now I have mg, and I'm going to distribute the 2mg to both places inside this parentheses here. mg plus, let's see, 2mg times 1 would just be 2mg minus 2mg cosine theta naught. mg plus 2mg is going to give us 3mg, so ultimately I have 3mg minus 2mg cosine theta naught. I'm going to pull the mg out of all those terms. I'm going to add together the 1 and the 2, which gives us 3 minus 2 cosine theta naught. And that is the tension in the string at the bottom of the swing. So there's a lot of work that goes into that. There's a lot of algebra, but this is a very interesting result. I don't think anyone would have predicted it would have been the weight times 3 minus 2 of the cosine of the initial angle. But the math says that that's what it is. I would recommend looking over these 4 problems, especially the math that goes into this to determining the initial height, and the algebra that goes into figuring out the tension down here. Those are problems that come up over and over again. To finish up, we're going to do one last problem with conservation of energy in springs. Now, this is a very easy springs problem. Okay, I will say that. This is an extremely easy one. They get more difficult when we have to deal with vertical springs, but we're going to start off with this one. We'll do a lot of these in class. The above picture shows a very poorly drawn spring that has one end attached to a wall and the other attached to a block of mass m. That would be right here. There's no friction between the block and the floor. Good, so we're not losing anything due to friction. The block is pulled a distance x from its initial position and then released. It doesn't say which direction, but let's say it goes in. Okay, so you're pulling the block backwards. In terms of the given variables and any fundamental constants necessary, determine, number 1, the initial potential energy of the block when it's at point x, and 2, the speed of the block as it passes its equilibrium point. So what we're saying we're doing with the block is we're going to pull it back a distance, let's say to right here. This is x. So the block is going to start off right there. Okay, it's pulled back a distance x. The initial potential energy of the block at x, well, that's really easy to find because the energy is added in its elastic potential energy, so US, by U pulling it back. So this is really simple. US equals 1/2 k x squared. I guess I didn't give you k. Yes, the spring, I should write that, with spring constant of k. Okay, so the spring has a spring constant of k. We pull it back. That's important for you to know. So US has to be 1/2 kx squared. The speed of the block as it passes through its equilibrium point, well, that means the block starts here, and as the spring pushes it back towards the unstretched length, I should say, as the spring pushes it back here, the spring is no longer as stretched as it used to be, so it's losing elastic potential energy, but the block is moving now and it's gaining kinetic energy. So we set up a conservation of energy equation, ET equals ET, no friction loss, so we don't have to deal with friction. The only two types of energy here are elastic potential energy and kinetic energy, and we're not dealing with the pulling back of it, we're just dealing with the release and when it passes through the unstretched length position. So on the initial side, we're going to write it initially has elastic potential energy, and on the final side it has kinetic energy. So that means that 1/2 k x naught squared, I'm just going to call it x because that's what they called it, is equal to 1/2 mv squared. We want to solve for v. That's pretty easy. We have a 1/2 on both sides. Those can cancel. We're trying to solve for v, so we divide both sides by m, take the square root. We end up with a speed of x, because taking the square root of x squared will just give us x, times the square root of k over m. X times the square root of k over m is the speed. So that's a very basic idea of how to deal with spring systems and conservation of energy. There will be much trickier ones. The pendulum example from before gives a good example of the things you can expect to see. We're going to deal a lot with this. This is a very big topic, energy conservation, especially in these situations. So if you have any questions at all, please don't hesitate to ask. This is the end of the energy notes. So the next thing we're going to cover in my notes is impulse and momentum. I'll see you guys then.